Okay, welcome to chapter 3. In this chapter, we're going to talk about the three measures of variability, which are range, standard deviation, and variance. And so let's do a quick review of measures of central tendency and discuss how they're different from measures of variability. So, central tendency is what we had talked about in chapter 2, and central tendency is an important descriptive statistic in all, variations, the mean, median, and mode. And what that descriptive statistic or what those descriptive statistics tell us is about the similarity between the scores. They give us one number that best represents those body of scores. And so they do that by reporting the mean, median, or mode. What's different here in chapter 3 is in variability, we're going to get numbers that tell us about the differences between the scores. So central tendency looks at the ways the numbers are the same, and variability looks at how they're different. And so some of the things that variability can help us sort out is how spread out are the scores in the distribution, also how close or far from the mean are the scores. And so, like I said, there are three measures of variability that we're going to be learning in this module, range, standard deviation, and variance. And for that, you're going to need your measures of variability worksheet, so kind of have it handy and off to the side. Okay, so the first measure of variability we're going to discuss is the range, and the range is symbolized by R. All statistical symbols are reported in, professional polished APA papers as italicized symbols. So that's why I have that R symbolized so that it's representing a statistical symbol. But anyways, the range is the measurement of the width of the entire distribution. And to calculate it, you just find the highest value in your distribution and subtract it from the lowest value in your distribution. So you can see the example here on your screen. The highest value in that distribution is 8 and the lowest is 2. So you just take 8 minus 2 and you would get your range of 6. This doesn't tell us a whole lot, just kind of a crude measurement of the distribution, but it's really the least useful measure of variability, and that's something that you're going to want to know for the quiz. That range is the least useful measure of variability in the same way the mode is the least useful measure of central tendency. Whereas the next measure of variability that we're going to discuss, standard deviation, is the most useful measure of variability. So make sure you are aware of that for the quiz as well. Standard deviation is the most useful and most used measure of variability, and that is analogous to the way that the mean is the most used measure of central tendency. So make sure you're aware of that. At any rate, the standard deviation is symbolized as SD. And it is a measure of variability that tells us the average amount that scores in a distribution deviate from the mean. Like I said, it's the most common descriptive statistic for variability, and there are two ways to calculate it. So there's the deviation method, which is the way that we teach people standard deviation so that they can understand the logic behind it. But then there is also the computational method, and it's called that because it's the one that we are going to use to compute through the standard deviation calculation. It's a shortcut. I'm going to show you a breakdown of that momentarily. But what you need to know from this screen is the note there that says standard deviations are never less than 0 because you can't have less than 0 variability. So it's important that you understand two things about that little bubble there that says note. The first is that if you do a standard deviation calculation and get a negative number, you have done your calculation wrong. It is impossible to get a negative number. The other thing that you should note from that is just the idea that you can't have less than 0 variability. If you can understand the reason behind that, it's going to help you understand a lot of the content in this course. So, because we spend so much time measuring variability, right? So, if you understand that you can't have a negative, it's going to help you understand why you're doing certain things in formulas as well. So the reason you can't have less than 0 variability is because things either vary or they don't. There's no such thing as negative variance. So if I am 39 and you are 29, then the variance between our ages is 10. there's never going to be a scenario where the variance between our ages is -10, say, because ages either vary, either, I'm older than you or I'm younger than you, and there's a variance there, or I'm the same age as you and there is no variance there. But there's nothing less than no variance. Okay, so as a reminder, the standard deviation is the average amount that scores in a distribution deviate from the mean. So think about what that means. If I get a score on my 50-point statistics test of 40 and the mean is 35, how am I within the average that people varied from that mean? Because not everybody scored at that mean, right? Not everybody got 35 on the dot. There's a variation in the scores. They're all over the distribution, right? So if I'm not right at the mean, then how far away from the mean is still like normal? What's like the normal range, right? And so that's what standard deviation tells us. If you look at your screen there, you see the normal curve, and in the middle is the mean. And so you see the two portions next to the mean blocked off in dark blue, and those portions are both one standard deviation away from the mean. And you can see there's a percentage inside of those dark blue portions, and that percentage says 34.1%. So 34.1% of the people scored between the mean and one standard deviation. And then also 34% of people scored one standard deviation below the mean. Okay, so what we're able to figure out is how many standard deviations people are away from the mean. So you could see people can be plus or minus 1, 2, or 3 standard deviations away from the mean. Okay, so the way I'm going to calculate the standard deviation using the deviation method is here on the slide for you, kind of as a cheat sheet. But I am going to go through it with you on the worksheet in more detail, and I think it's easier to understand if you just see it. So I'm going to go over this slide pretty briefly, and then hopefully I'll break it down for you in a way that's more understandable on the worksheet. But at any rate, this is the deviation method, which is used as a teaching method to help clearly understand the concept, like I pointed out. And so the formula for the deviation method is written out completely there in that formula box on the left. And it says that you can find the standard deviation by taking the square root of all the added up scores of each raw score minus the mean and then squared, and then added up, right? Divided by the number of scores in your data set, or n. Once you have that, you take the square root, and that's your standard deviation. A shortcut way of writing that, but it's the same exact thing, is to just condense the part in the parentheses to a little x. So little x, or lowercase x, is representative of what we call the deviation score. It's the symbol for the deviation score. And we remember that capital X is the symbol for raw scores, or for each raw score. So if you look at the formula in the parentheses on the left, you see x minus m. X minus m is the formula for calculating that lowercase x, which is the deviation score. So to the right, in the shortcut formula, that parentheses has just been condensed to a lowercase x, but you're still doing the same exact process. So to calculate your standard deviation using the deviation method, you're first going to find the mean, and then you're going to subtract the mean of the distribution from each score. And that's going to give you that lower x, that deviation score, that looks at each person that took the quiz, how far away from the mean of the quiz was each person. So what that's going to leave you with is a bunch of little x's, or deviation scores. And those deviation scores, if it's a normal curve, should be positive just as much as they are negative. So I should see an equal number of positive deviation scores on the right side of the curve, and I should see an equal number of negative deviation scores to the left of the curve. So now I have all these numbers, and some of these numbers are going to be negative to represent that left side of the curve. And so I know I can't have less than 0 variance. To correct for that, I'm going to square all of the scores. I can't just square the negative deviation scores. I have to square them all. I have to treat them all the same. So after I square all of them to get rid of those negatives, I'm going to add them all up and divide by n. the n is going to account for everyone in the study. And then after I do that calculation or that division, I'm going to take the square root, and taking the square root essentially undoes the squaring of each deviation score, right? We had to square it to get rid of that, those negative numbers, because you can't have less than 0 variance. And so when we square it, we then on the back end unsquare it by taking the square root. I don't know if any of those words are grammatically correct, but I'm leaving it in. Okay, so what we're going to need now is our measures of variability worksheet, and I'm going to give you a demonstration of calculating through the deviation method to get standard deviation. Okay, so this is the measures of variability worksheet, and here we actually have two separate data sets. And so I like to label this data set that's on the left of this line here, data set A, and then I like to label this one over here B, and just draw a line so I'm clear that these are two separate data sets. You can even go as far as folding your paper if you want to. In fact, let's do that. Okay. So on this side of the worksheet, you see two sections. The top section is titled Deviation Formula, and then the bottom section is titled Computational Formula. I'm going to start by showing you the deviation formula. And this formula is the one that we use to teach the concept of standard deviation to help give people a better understanding of kind of the methodology behind a standard deviation and what it represents. But we in this class are actually going to use this shortcut formula, the computational formula. But for some of you, learning the deviation formula is going to make this whole standard deviation situation a lot clearer to you. If it doesn't, just disregard it. Don't worry about it. Okay, so for the deviation formula, the standard deviation is sigma and then a lowercase x squared, and that's divided by the n, and then you don't take into account the mean. Whereas with the deviation formula, we have a capital X, and we have n, and then we don't have the mean squared in the deviation formula, where we, do have it in the computational formula. So we don't have it in the deviation formula, but we do have the mean in the computational formula. Okay, so the difference between the small x and the big X is this little x is a deviation score. That's what this symbol represents, whereas in this case, it represents a raw score. So this is saying add up all your squared deviation scores, and this is saying add up all your raw scores that you've squared. So for the deviation score, the way we get little x is by subtracting the mean from each raw score, and that is why the mean is not represented in the formula, because it's taken into account for each individual score. So this step we actually skip in our computational formula. We just square them, add them up, and divide by the mean, subtract the mean instead of going number by number and subtracting each score, the mean from each score, so we can see what that variation is per person. But at any rate, that's what we're doing here. We're taking person one's score of 100, and we're subtracting the mean. So they calculated the mean for us, but obviously we would calculate the mean by adding up all the raw scores and dividing by the number of numbers, which in this case is 8. There's 8 scores here, so 672 divided by an n of 8 is going to get us 84 as our mean. And so then that's why we are subtracting 84 from each one of these scores, so that we can see the variance between the mean and each person. So how far away from the mean was each person? This person was 16 points away from the mean on the positive side. They got the highest score. Whereas this person was 19 points away from the mean on the negative side. So they were 19 points below the mean. So after you get the individual variation, or what's called your deviation score, then we have to square it, because as you know, you can't have less than 0 variance. That's not possible. Things either vary or they don't. So you have to square all of those to make the whole methodology work. And so when you square all of those, you get these values here. So 16 squared is 256, 13 squared is 169. So each deviation score squared, and then you add all those up and you get 1010. That goes in your numerator. The n is 8, and so we had to square the numbers to get rid of the negative numbers because you can't have less than 0 variance, and standard deviation is a measure of variance. So we had to square them to get rid of the negatives, and now we have to square root them to undo what we did with the squaring, basically. So when we do our division here, we get 126.25. This is our variance. We'll talk about that more coming up. But we do the division, we get this variance, and then we square root it to correct for squaring all the raw scores. And then we get this unrounded value and our final answer of 11.24. Okay, so maybe that gave you some more clarity on what the standard deviation is, but if not, that's okay, because we don't use that method anyways. We use the computational method. It's a shortcut. Basically, we eliminate 2 steps from the deviation method, and so this is the one that we're going to use in our class. And the difference is that we are not going to calculate the deviation score. Instead, we're just going to square each raw score, add them up, divide by n, and then subtract that from the mean squared and take the square root. Okay, so go ahead and grab your measures of variability worksheet back out, and we will do a demonstration of how to calculate through your standard deviation formula for the computational method, which is the one we're going to use. So this formula here, the computational formula, is the formula that we use. So I'm going to write a note to myself that says use this formula. So this deviation formula here is used to teach the idea behind standard deviation, but it involves these 2 extra steps. So the computational formula is a shortcut, and it's faster, so we're going to be using this one. But the point of this square here is to show you that whether you use the deviation formula or the computational formula, you're going to get the same standard deviation. So the computational formula tells us to first square all of our raw scores and then add them up, divide that total by n, and then subtract the squared mean and take the square root of that answer. So to do this numerator here, we're going to go through and we are going to square all of our raw scores. This is telling me to square all of my raw scores. So again, these 2 columns here are used in the in the deviation formula. It's a longer method that teaches you about the idea of standard deviation, but we are not going to be using these 2 in our shortcut, faster computational formula calculation. So if you go through and you square all of the raw scores, you would see the result of that here. So a score of 100 squared is 10,000. A score of 97 squared is 9,409. A score of 93 squared is 8,649, and so on. The next step of the formula is telling me to add all of that up. So if I go through and add up all these scores that I've squared, I get 57,458. And you'll notice that that value is placed here in the formula. It's the numerator. The next step in the formula is to get the n. The n is the number of scores I have. So if I count these 1, 2, 3, 4, 5, 6, 7, 8, I'm going to end up with an n of 8. So I could put that down right over here is the denominator. And the next step is to calculate my mean. And so in order to calculate my mean, I need to add up all my raw scores and divide by n. So we had already determined that n is equal to 8. So I'm going to go ahead and put that there. So if I am to do this mean calculation and I add up all the scores, I'm going to get 672. If I divide that by 8, I'm going to get a mean of 84. So I'm going to put 84 here. and then the squared symbol after it, and I'm ready to start calculating through this formula. So when I do the division, I get 7,182.25. When I square my mean of 84, I get 7,056. And when I subtract those two numbers, I get my variance, which is 126.25. So the way we calculate variance is simply to identify it in our standard deviation formula. And so your variance, or V as the symbol is going to be this number here under your square root symbol while you're calculating through your standard deviation formula. So all you have to do to calculate variance is just spot it. There's actually no calculation that's extra outside of running your standard deviation calculation. So that's going to be our variance. And then when we take the square root of our variance, we're going to get an unrounded standard deviation of 11.236. I'm going to look at this third digit to decide what to do with my second digit after the decimal. And this third digit is a 5 or higher, so 6 is higher than 5. So that means I'm going to dump it and raise my second digit up one value. So my final standard deviation is 11.24. And just as a note, if you had a standard deviation, you could square it to get the variance. So standard deviation squared is going to give you your variance, but we just, for the most part, are going to take, well, not the most part, every part, all the parts. We're going to take the number under the square root, and that's going to be our variance. And then the way, so our standard deviation is 11.24 with correct rounding. We got our variance, and then the only measure of variability left here is the range. Then the range is just a crude subtraction of the raw score. So 100 minus 65 is 35, and that's the range. Okay, so let's go ahead and do this B data set here. Actually, let me see. It's easier to see everything. Not so cluttered. Okay, so for this, we're going to go through our standard deviation formula. And so I'm going to write it out, and then I'm just going to start collecting my puzzle pieces. So the first puzzle piece is sigma x squared, which is telling me to square my raw scores and then add them up. And so if I were to square 100, I would get 10,000. If I were to square 98, I would get 9,604. When I square 96, I get 9,216. When I square 94, I get 8,836. When I square 92, I get 8,464. When I square 90, I get 8,100. When I square 89, I get 7921. And 87 squared is 7569. Okay, so then the next step is to add up all these squared values. And when I do that, I get 69,710. So 69,710 is my numerator. I'm gonna write that in the numerator spot. And then I have to get my n. So I'm just gonna count my scores. 1, 2, 3, 4, 5, 6, 7, 8. So n is 8. I'm going to put that there. And then I'm going to calculate my mean. And to calculate my mean, I need to add up all the raw scores, which is going to be 746. And then divide by 8. So 746 divided by our n of 8. And 8 is just the number of numbers we have. Going to get a mean equal to 93.25. So now I can put the mean in the mean spot of the formula and throw the squared symbol after it, and I'm ready to calculate through. So if I, let me put my square root symbol so I don't forget it. If I do the division, I'm going to get 8,713.75. And that's going to be, we're going to subtract the squared mean from that. So if I square 93.25, I get 8,600 95.56. And then if I do the subtraction there, I'm going to get my variance, which is which equals 18.19 when I do this subtraction. So just down here, I should have made a spot for it, but I didn't. So we're just going to put it down here in the variance line I just created, 18.19. Let's do a standard deviation line too, just for clarity purposes. So then when I take the square root of my variance, I'm going to end up with my standard deviation, which is going to be 4.26 with correct rounding. And so I'm going to put 4.26 on this standard deviation line I just created. And my last measure of variability that I need to calculate is my range. So to do that, I am going to take 100, which is my biggest number minus my lowest number. So my highest minus my lowest gives me my range of 13. And that is the measures of variability worksheet. So variance is the next measure of variability we're going to discuss, but we did just mention it on the tutorial of the measure of variability worksheet. So this is kind of a refresher, but this measure of variability called variance is symbolized by a V, a capital V, and it's the measure of how spread out a set of scores are. It's also called the mean square deviation because it's the average of all the squared deviations from the mean. So if you go back and look at the deviation method, you'll be able to see why it's called the mean squared deviation, because like I said, it's the average of the squared deviations from the mean. So to calculate variance, you calculate the standard deviation and then you just don't find the square root. And so the number under the square root is your variance. The variance is equal to the standard deviation squared. However, because of the way we round, so specifically for our purposes, I ask that you don't calculate the variance that way because we might get different numbers. It's more of an approximation than an exact, and we need exact for putting our values into Canvas. So to calculate the variance, we're not going to square the standard deviation, but instead we're just going to calculate through our standard deviation, and then we are going to identify the number under the square root, and that's going to be our variance. Sometimes students ask me if the variance is just the square root of the standard deviation, why would we use it? And the answer is that some formulas require using the variance rather than the standard deviation. But we don't have any formulas in this class that use variance, so we don't have to be too concerned with it. In fact, I'm racking my brain right now thinking of any formula that I use that has variance in it, and I can't think of one. So it's not used very often, but it does exist in some formulas as being necessary over the standard deviation squared. Okay, so we're switching gears a little bit here, and what we're going to do is kind of talk about ways that we can display variance on a normal curve. And we're also going to start to think about like visualizing, comparing our data sets. You know, pretend you're a statistician or a researcher and you're going to do your own research on people. Maybe you want to see if meditation makes people more empathetic or something. And so you do your own sample, you get your own numbers, and you can now visualize yourself graphing those numbers on a distribution like you did for the graphing homework by making a frequency polygon or a histogram. But at any rate, you graph that data that you collected from your study on meditation. And then you have all those numbers kind of displayed there visually. And now you might want to come up with different labels for where those scores fall on your curve. And we see this happen all the time with, medical professionals and education. We use percentiles to kind of show how one person's score compares to other scores. And so I remember when my oldest daughter was like 6 months old, I took her to the doctor, and he said that her body weight was at like the 15th percentile. I'm a pretty small person, and so she has my genes, and she's pretty small. But her head was at the 85th percentile. So that was kind of a funny discrepancy to me as a statistician. She had a big old head and a tiny little body. She was so cute. She's older now, but At any rate, so percentiles kind of allow us to see how the scores that we have, my daughter's body weight, how that compares to everyone else. And so for percentile, this is the point on a distribution where a given percentage of scores fall below. So if I'm told my daughter's body weight is in the 15th percentile, I know that only 15% of the population of kids at her age have a body weight that's less than her. Whereas with her head being at the 85th percentile, that means that 85% of people her age had a smaller head than her. So a percentile is just a way to kind of divvy up a normal curve as if you would divvy up a pie. And then you label the pie. As you get 1/8 of the pie, you get 1/3 of the pie. It's the same idea here. You're saying, this is the first percentile, second percentile, so on and so forth. So I'm going to be showing you a visual representation of everything I'm saying coming up. I just kind of want you to start thinking of if you have a normal curve, and that normal curve serves as your basis of comparison. So you're going to compare your meditation scores against that normal curve. I'm going to compare my daughter's head size against that normal curve and see that it's, bigger than 85% of other people. So we're taking our data sets and we're comparing them to the normal curve. We just want to have ways to communicate what our scores mean against that normal curve, and so where those scores fall on that normal curve. And so that's what these terms that we're talking about now represent, just different ways to dice up your normal curve and then label those chunks or label those pieces of the pie as different terms. So percentile, quartiles, deciles, so on and so forth. All right, so we kind of talked about percentiles already, but just to solidify it further, 95th percentile, so if you were told that you scored in the 95th percentile on a quiz, that means that you did better than a lot of other people. A lot of other people got scores below yours. And then if you scored in the 5th percentile, this would mean that very few scores fell below your score. And so you did not so great on that quiz. All right, so percentiles are used to show various forms of range. And one thing that you want to note, because on the quiz, you're going to be asked to solve word problems, understanding some of the fundamentals of the normal curve. And so one of those fundamentals is that the 50th percentile is right in the middle of the curve, right in the middle of the distribution. And so it is always going to be equal to the median. So if you know that the 50th percentile is always equal to the median, and I give you a word problem where I say, hey, Johnny scored a score of 35, and that was right at the 50th percentile. What's the median? You would know that the median is 35 because the score at the 50th percentile is always going to be equal to the median. Okay, and then kind of reset mentally the normal curve or the pie in your mind. And now imagine dividing it up where with percentiles we just divide it up in ones. Imagine dividing up a pie or, for our class, a normal curve into quarters. And so the first quartile is going to coincide with the 25th percentile. And then the second quartile is going to coincide with the 50th. The third quartile is going to coincide with the 75th. And then we never talk about the fourth, but it would coincide with the 100th. So that is how we can divide up a curve and label it with quartiles, by dividing it up into quarters. Okay, so then you have deciles. And deciles divide a distribution into 10. So if you cut it up in 10 pieces and labeled each piece, in order of magnitude, you would have the first decile, second decile, third decile, fourth decile, all the way up to the 10th decile. And something to know for when you're solving word problems regarding the normal curve and these areas, the deciles, the percentiles, quartiles, the first decile is always going to be equivalent to the 10th percentile. The second decile is always going to be equivalent to the 20th percentile. The third decile is always going to be equivalent to the 30th percentile, and so on and so forth. And then the lowest score is going to be in that first decile, and the highest score is going to be in your 10th decile. So if on a word problem I say to you, the lowest score is 20, what decile does that fall in? You would say it falls in the first decile. Okay, so also we've calculated range for measures of variability, and that's just taking the highest score from the lowest score. But what if we wanted to know the range of just the middlemost 80% of the curve, or just the middlemost 50% of the curve? We could divide our curve up like that, and then that, of course, has its own term. So if we kind of block off the middlemost 50% of the distribution, and we take the highest score in that middlemost 50% of the distribution, and we take the lowest score in that middlemost 50% of the distribution, and we subtract those two scores. The result, the value that results, is going to be our interquartile range. So it's the middlemost 50% of the distribution, but you can find it by just blocking off the first and third quartiles, and then getting the score at the first quartile and getting the score at the third quartile, subtracting those scores, and that's going to be your interquartile range. And then for the interdecile range, it's the middlemost 80% of the distribution, so you just need to find the difference between the scores at the first decile and the score at the 9th decile, and that's going to constitute your interdecile range. So let's go ahead and take a look at the worksheet now. I think it'll give us a better understanding of all these terms I just mentioned. Okay, so this is the percentiles, deciles, and quartiles worksheet, and what you're looking at here is the normal curve. You could think of the normal curve as like a template. We use it as a standard of comparison. And so when we plot most of our scores and create a visual, distribution like this, it normally takes the shape of a normal curve. Our data set, when we plot it, connect the dots, normally takes the shape of a normal curve. And because of that, this is our standard of comparison. So what we're talking about on this particular worksheet is a bunch of different ways to label the curve. We can divide it up as if we were dividing up a pie into different proportions, and then we label those proportions with different terms. So the first term you need to know, so we're dividing up the curve, and the first term you need to know for labeling is called percentiles. And so percentiles are labeled on the x-axis as basically in ones. So you have first percentile, second percentile, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th. Here on this worksheet, they're blocked off in tens just because there's not enough space to write all the ones out. But percentiles are dividing the curve up into ones, and you can see this is going to mark the 10th percentile here. This is going to mark the 20th percentile here, 30th, and in between, you have 31st, 32nd, 33rd, 34th, 35th, so on and so forth, right? And then, so kind of putting that aside, taking that out of your mind, and now you have a fresh normal curve, not divvied up at all, and you think, okay, how else could I divide this up? And you think, oh, I could divide it up into tens. So if you divide it into tens, it's called deciles, and this first line here is your first decile. One of the things we know from lecture is that the lowest score in our distribution is going to be in the first decile over here, right? This is the first decile here. So then we have the second decile, the third, fourth decile, fifth, sixth, seventh, eighth, and ninth, right? So it's marked off in tens, and you can see that the 10th percentile is equal to the first decile, and that will always be the way it is. That is unwavering because this normal curve is our standard of comparison. It's a template, it's unchanging. So first decile is equal to the 10th percentile. 50th percentile is equal to the 5th decile. And then we have quartiles. So again, return the curve mentally back to whole, and then think of dividing up the curve in quarters. So 4 pieces. So the first piece here is going to be at what would be the 25th percentile. Okay. And then the second quartile is going to be equal to the 50th percentile and the 5th decile. The third quartile is going to be here in between the 70th and 80th, so that would be the 75th percentile, in between the 7th and 8th decile. And then of course the fourth would be over here at the 100th percentile mark. And so when you're looking at the normal curve, you're the researcher, you're the statistician, and generally, because this is your standard of comparison, what's going to happen is you're going to have done research on your own sample and you're going to have your own data. And on the x-axis of the normal curve, instead of putting percentiles and deciles and quartiles, what you're going to be putting is your raw scores. So let's say these are all the raw scores of my students over all the years that have taken quiz 1, okay? And so here are their raw scores. You see it symbolized by X. Here's the frequency count going up to 500 students. And so you could see about how many students got each score, right? So what I can do is I could take my normal curve template and I've put it on this transparency so that we could do this, because this curve, this is our standard of comparison. This is our template. It's unchanging. So if I put it on top of my specific data set, I can see how my scores on my data set line up with the percentiles, deciles, and quartiles. And so I can see, okay, if I got a 30 on the quiz, that's going to be right here on my distribution. What does that equal to on my normal curve, my standard of comparison? So 30 is equal to the 50th percentile. 30 is equal to the 5th decile. The score of 30 is also equal to the 2nd quartile, okay? If I asked, what's a score of 15 at? So here's my 15. If I line it up with my normal curve, a score of 15 is at the 20th percentile, or the 2nd decile. So knowing that my scores are going to line, as long as my distribution that I sampled is normal and creates a normal curve, then I would be able to identify where scores are at on that normal curve by using these labels, percentiles, deciles, quartiles. And so that will help me to be able to solve these word problems down here. Also, knowing where the interquartile and interdecile range are will help me to solve word problems that are asking me for information on percentiles regarding specific scores or deciles or quartiles. One of the terms that we learned with our measures of variability was range, and we know range is just the highest number minus the lowest number. And now we're going to have these two other types of range, interdecile and interquartile. So what you really want to note is that the interdecile range is going to make up the middlemost 80% of the curve. So you might want to write yourself a note that the interdecile range takes up the middlemost 80% of the curve. So if I were to draw the interdecile range, it would be the middlemost 80% of the curve. So it would be from this spot on the curve to this spot of the curve. So this is going to be the middlemost 80%, and it is called the interdecile range. So what that means is that it makes up all this portion of the curve here. I don't know why. Okay, so from here to here, the interdecile range, everything in the shaded area here, but not the tails. So any numbers that fall in the interdecile range are going to be numbers that constitute the 80% middlemost portion of the curve. And then we have the interquartile range, which is going to make up the middlemost 50% of the curve. So I'm going to write myself a note so I don't forget that. Middlemost 50%. So we're just talking about different ways to divide up the curve, chop it up, look at it from, just from this point to that point. So the middlemost 50% of the curve is going to be from here at the 25 to the 75. Okay, so let me draw a line to symbolize that. And this is going to be my interquartile range. Okay, so this is just the normal curve, just a mesokurtic shape. Remember, our normal curve is our standard of comparison. So when we have the normal curve, if we divide it up like this by blocking off the middlemost 80%, that's called the interdecile range of the normal curve. If we just look at scores here in the middlemost 50%, we're looking at what's called the interquartile range. Okay, so the interquartile range would make up this part here in pink. Okay, but not this area here. That was the interdecile range and not the tails. So the interdecile and the interquartile overlap in the middle, and then not kind of out towards the tails, and then all the way in the tails. They're different. Okay, so what you're going to be asked to do is to read these word problems and then identify what types of range, what scores constitute certain types of range, what scores correspond to the 50th percentile, the first decile. So you need to be able to do this for quiz 1. Okay, so we're going to use what we know about the normal curve to answer this word problem. And so it says on a college placement test, the median score was 50. So I know that here it also says 50 and that's the median, but this is as a data set, much like, our pretend data set that I was showing you here, right? So this is a pretend data set that I said is, my students' quiz scores. And this is a pretend data set about a college placement test. And the median score happens to be 50, but it's not always, and the score is not always the same as the percentile. Usually it isn't. It just is in this case. So it says the median score was 50. And what I'm actually going to do is start pulling out my puzzle pieces here so that I can refer back to them when I'm kind of solving through this word problem. So it says the graph distribution was a mesokurtic shape. So I know that I can use my normal curve as a standard of comparison with this data, because this data also, when it's plotted, takes the mesokurtic shape. So we can compare them. It says the highest score was 80 and the lowest score was 20. 80% of the scores were between 25 and 70. 50% of the scores were between 40 and 70. So the first question is, what is the interdecile range? And just to be clear, it's the same way that you would calculate the actual range, just with a specific set of numbers from the middlemost portion of the curve. But if we were to calculate the actual range, we would take the highest score of 80 minus the lowest score of 20. So we would take 80 minus 20, and our actual range would be 60. So the range from here to here on this sample data set is going to be the actual range. Okay, so what is the interdecile range? Well, I know that the interdecile range constitutes the middlemost 80% of the curve. So if I refer back to my worksheet, it says that 80% of the scores were between 25 and 75. So I'm going to calculate my interdecile range by taking the highest score in the 80% of scores minus the lowest score. So 75 minus 25 is going to equal 50. So my interdecile range for A is 50. And then what is the interquartile range? Well, I know that the interquartile range is the middlemost 50%, and it says 50% of the scores were between 40 and 70. So I'm going to subtract the highest number of the 50% middlemost of the curve from the lowest. So 70 minus 40 equals 30. And so 30 is going to be my interquartile range. And then what score corresponds to the 50th percentile? Well, one thing I know is that the median score is always equal to the 50th percentile. So if I know the median, then I know the score at the 50th percentile because they're one and the same. So it says the median score, which remember the median score is always equal to the 50th percentile. So the median score was 50. So what corresponds to the 50th percentile? What score corresponds to the 50th percentile? 50. The number at the median. And then what score is in the first decile, I think is a little clearer than the word corresponds. So what score is in the first decile? I'm going to change it to that. What score is in the first decile? And the lowest score is always in the first decile. So the lowest score in this case is 20. The lowest score was 20 in the whole distribution. So the lowest score is going to be the score that's in the first decile. So that's 20. So I don't know if you remember chapter 2 when we discussed kurtosis, but we talked about how if you have your data set and you plot all your numbers like you did on your graphing worksheet, and you connect all those data plots, and it takes a shape of a bell or the normal curve. We call it mesokurtic. If it's leptokurtic, it's kind of tall and skinny, and if it's platykurtic, the shape of that distribution is going to look almost like flat and kind of squarish, rectangular-ish. So if I show you a picture of a leptokurtic shape, you'd want to be able to identify that shape for the quiz as leptokurtic. But you also want to be able to describe the shape of a distribution just by having its range and standard deviation. So not having a visual picture, but just some numbers, and being able to figure out what shape the distribution is from those numbers. So that's what we're going to be talking about on this slide. It's called assessing kurtosis, and we use what's called the 1/6 rule to quickly evaluate the kurtosis of any unimodal symmetrical distribution. So that's going to be any distribution that has one mode or one number occurring more than any other number, and the distribution is symmetrical. So while the leptokurtic and platykurtic shapes are not normal curves, they are in fact symmetrical and unimodal. So the way that we would go about assessing kurtosis just using numbers is first we would want to look at the given range, and we would say, okay, if this is our range and we divide it by 6 using the 1/6 rule, the standard deviation we would get would be x, whatever it is. And then once you have what the mesokurtic standard deviation would be, if the shape was a normal curve, then you can compare the actual standard deviation from the data set to what the mesokurtic standard deviation would be. And from there, you kind of can determine if you have a leptokurtic, platykurtic shape, or if you, in fact, do have a mesokurtic shape. So what you need to do that is you start by taking the range that's given, and you divide the range by 6 to get the approximate standard deviation. You're also going to be given a standard deviation, and that standard deviation is the actual standard deviation of your data set, which we're going to compare against our normal curve, right? So if you had a distribution and the range was 600, if you divide that by 6, assuming that this distribution is normal, you would get a normal or mesokurtic standard deviation equal to 100. 600 divided by 6 is 100. So if this data that has a range of 600 is a normal curve, then the standard deviation would be 100. So then I would look at my data set standard deviation and see if it is 100, and if it is 100, then my distribution is going to be a mesokurtic shape when I plot it, or a shape of the normal curve. But if my standard deviation is less than 1/6 of the range, or less than that mesokurtic standard deviation of 100, I have a leptokurtic distribution. So if I calculate my mesokurtic standard deviation, I see that it's 100, I look at my data set, and then I go, oh no, my standard deviation is 50. That's less than what a mesokurtic standard deviation for this range would be. I must have a leptokurtic shape. And then you could do the same if you ended up, calculating the standard deviation for a mesokurtic shape with a range of 600. You say, okay, that would be 100. So if this distribution is normal with a range of 600, the standard deviation should be 100. But then you look at your data set and you see that your standard deviation is actually 200. So you know you don't have a mesokurtic shape, because if you had a mesokurtic shape, your standard deviation would be 100. But it's not, it's 200. So that is more than 1/6 of the range. And if you have a standard deviation from your data set that is more than 1/6 of the range, or of the mesokurtic standard deviation, so more than the mesokurtic standard deviation, like here with a standard deviation of 200. In that case, you have a platykurtic distribution. So I'm going to show you this now, so you'll need to go ahead and grab that percentiles worksheet back out. Okay, and then we have using the 1/6 rule to evaluate kurtosis. And so what we need to remember is that if we're given the range and the curve is a normal shape, we could approximate the standard deviation by dividing that range by 6. So what we can do, taking that kind of a step further, is we can, if we're given the range, we can estimate the mesokurtic standard deviation and then look at the actual standard deviation and compare it to what the mesokurtic standard deviation would be. And if the standard deviation is less than the mesokurtic standard deviation, we have a leptokurtic shape. And if the standard deviation is more than the mesokurtic standard deviation, we have a platykurtic shape. So I'll show you what I mean, but the first step in doing this is to always first calculate what the mesokurtic standard deviation would be. So don't look at these standard deviations, because these standard deviations are from a specific data set. But we're just talking about the general, theoretical, normal curve. If I have a range, I can divide it by 6 and get the standard deviation on that normal curve. Which is, of course, a mesokurtic shape. So I'm going to start by just looking at the range and calculating my mesokurtic standard deviation. I'm going to abbreviate that. So I'm going to do that for each one of these. So mesokurtic standard deviation, mesokurtic standard deviation. Okay, so I'm able to calculate the mesokurtic standard deviation for A because I'm given the range. So if I take a range of 24 and divide it by 6, I'm going to get a standard deviation equal to 4. If I look at B and I take a range of 36 and divide it by 6, I would get a mesokurtic standard deviation equal to 6. Then for C, if I take my range of 90 and divide it by 6, I would get a mesokurtic standard deviation of 15. So what I've done is taken the range of each of these different data sets and divided it by 6 so that I could see what the standard deviation would be if this is a normal curve. But now what I'm going to do is look at the actual standard deviation for each of these example distributions here and compare it with the standard deviation that I just calculated. I know that if this shape is mesokurtic, if the curve for this data is mesokurtic in shape, then the standard deviation should be 4. So let's see what the standard deviation is. The standard deviation is not 4. The standard deviation is more than 4. So when the standard deviation is more than the mesokurtic standard deviation that you just calculated for each of these, which in this case is 4, then you have a platykurtic shape. So if the standard deviation of the data set is more than the mesokurtic standard deviation, you have a platykurtic shape. Okay, let's look at this. So we know that for a range of 36, if it's a normal curve, the standard deviation should be 6. But here we have a 3, which is less than a normal curve standard deviation of 6. So I know that this shape is not normal. When the standard deviation of your given data set is less than that mesocritic standard deviation that you just calculated, then you have a leptokurtic shape. Less leptokurtic. Okay, and then finally, for a range of 90, a mesocritic standard deviation should be 15. Let's see what this sample's standard deviation is. It is 15, so I know that this one is a mesocritic distribution because the standard deviations match. So mesocritic. Okay, and just to look at this from a couple other ways to kind of cement your understanding. Number 2 says a mesocritic distribution with a range of 120 has an approximate standard deviation of what? So it's a normal curve with a range of 120, and I know that I could approximate standard deviations from the range of a normal curve by dividing it by 6. So 120 divided by 6 would give me a standard deviation of 20. And then number 3, if a given mesocritic distribution has a mean of 100 and a standard deviation of 15, what is the approximate value of the range? Well, all I need to know is the mesocritic distribution and the standard deviation. The mean is really neither here or there, it's just kind of extra information. But if you give me the standard deviation and tell me it's normal, I can just kind of work the opposite way to give you what the range would be. So I'm going to take my standard deviation and multiply it by 6 instead of taking my range and dividing by 6 to get my standard deviation. Take my standard deviation and multiply by 6 to get my range. And when I do that, I should get 90. So you could check your work by doing, okay, let me take the range and divide it by 6 to make sure I get a standard deviation of 15. And you would. Okay, so that is the percentiles, deciles, and quartiles worksheet. All right, and that is it for chapter 3. Thank you for listening all the way to the end. I will talk to you on the next one. Have a great day.